slide that shows kind of your overflown stack going from left to right. You overflow the saved frame pointer, and then you smash the return address, which is your saved EIP, and then right after, so basically, if you return from that overwritten EIP into a function, like at the top of the function implementation in a shared library, it'll pull off an argument from that following it. So that's the return 1 arg. And then when that function is done, it'll return to return address 2, which will pull return 2 argument off the stack. And basically, you can use this to call any functions that take one argument over and over again. And so what this stub does is, like I mentioned, you just basically take it, align it with EBP and EIP, and it just encapsulates all of this logic that will return into setJump. And the main idea is, so because there's no ASLR, you can choose addresses at will, and we can return into setJump, and we'll just choose a writable memory address. And so I just use a memory address in the writable data segment of DYLD. So what that does is that basically writes the value of all our registers to this hard-coded memory address. Because we've also overwritten the saved EBP, that's one register that we can control. So I can return into setJump, which will write all my registers to a piece of memory, and then return from there to that memory, and it execute the value of the EBP register as CPU instructions. So that gives me 4 bytes of controlled executable bytes. I'll basically do this a couple times to gain more control, and then finally we'll return into stirdup, which takes a string and copies it onto the heap and returns that buffer, and we'll call stirdup on the rest of our attack string, which contains our payload, and then execute that instead. So to kind of go into a little more detail, like I said, there's an implementation of setJump in DYLD, so we can hard code that address, and we'll know where it is for that version of OS 10. So we're going to jump into that, copy all our registers to a chosen writable address. We're going to return to 24 bytes past that writable address to execute 4 bytes from the value of the EBP register. And because x86 code is so compact, those 4 bytes actually let us do something useful. We need to adjust our stack pointer to make everything work. So we'll just adjust ESP, and then we'll execute the pop A instruction. The pop A instruction will basically load all the CPU registers from the stack pointer. So it'll, from our attack string, load up more registers, and then I'll execute ret, so that the ret to return to the next address on the stack. And so this lets us kind of keep bouncing along. And at the end of this buffer on the first screen here, I have the 12 bytes of x86 code. So those are actually, when you execute the pop A instruction, it'll load that memory into registers. I think if I recall correctly, it's the EDI, ESI, and EBP registers. Yeah. So, and this time, we're going to do the same thing. We're going to jump back into setJump again, and then return into our jump buff, and that'll give us 12 bytes to execute of chosen instructions. What this does is, again, it has to adjust our stack pointer just to make everything work out correctly. And it's going to take the address of ESP plus 0xC, which is essentially the pointer to our payload that follows the stub. And then it's going to push that onto the stack so it can be used as the argument to the next function that we're going to call. Overflows on QuickTime are a little more difficult to do, but that doesn't really stop anything because QuickTime also has plenty of heap vulnerabilities, and heap protection is not exactly something that Apple can just build into one binary. It requires actually changing the system-level heap. So let's move on to how Apple's heap is created. And what I say about their heap is that its level of security is very 1999, which is essentially true because they wrote it in 1999, and just haven't really changed it since. So they call it the scalable zone heap allocator because it grows the heap by different size zones. So depending on the size of your allocation, it's basically divided into multiple sub-heaps. So for instance, if your allocation is under 496 bytes, it'll go to what's called the tiny heap. And if it's a little larger, it'll go into what's called the small heap, or large and huge, respectively. And the way that it does this is each heap is divided into fixed-size blocks that it calls quantum, or quanta, be plural. And it will, any allocation is rounded up to the nearest, or to the next largest quantum size for that region that it's assigned to. And so basically, why you need to know this is depending on the size of buffer that you're overflowing in a heap overflow, that'll change how the heap actually behaves. And for the tiny and small, most of the buffers that you'll overflow are going to be under 16K. And so basically, they operate mostly the same. So these are where we're going to focus a lot of our attention. And also because everything above that is a little more custom there. Instead of using fixed-size quanta blocks, they just allocate pages directly. So it's less like a heap and more like sort of just relying on the operating system memory allocator. So like other heaps on Windows or older ones for Linux, they have a system of free lists to basically organize free heap blocks. And if there's a memory allocation for a buffer of a similar size, it'll allocate it from the free list. It'll allocate it from the free list instead of assigning it to a new heap. So these free lists are stored in a free list array of 32 elements, and basically that organizes all the free blocks based on size into, based on their multiple of the quantum size. So for instance, this picture shows the tiny region free list array. And so there's, on the left we have the array, which is basically going to be 32 elements, 32 elements. And for instance, the first one is allocations up to 1 times the quantum size. The second element is 2 times the quantum size, and so on. And then the last element in the array is anything larger than 32 times the tiny quantum size. And each of these array elements point to a linked list. And these linked lists are all the free blocks. And so the important thing to understand and remember about heap overflows is that these linked lists are not external to the heap allocations. These are in the heap blocks themselves. And so this is the crucial vulnerability of kind of the classical heap overflow, is that these pointers that link the linked lists are in an attacker's reach. If you overflow one buffer into the next, you are overwriting, and that next heap block is a free block, you are overwriting this heap metadata, the previous pointer, the next pointer, and the block size. So, like I said, basically, this metadata is stored inline, which is basically the source of most memory corruption vulnerabilities. For instance, Stack Overflows have inline return addresses inline with data. Those can get overwritten. Heap overflows have inline heap metadata. Those can get overwritten and corrupted. And so basically what you're doing is you just basically overwrite the heap from the overflown buffer, hoping to find a block that is considered a free block, and that's once you can overwrite the previous and next pointers. And in practice, what you'll do is just have your values for previous and next just repeated 1,000 times, so that if any of those are aligned on a free block that gets removed from the free list, you will actually gain control or perform the 4-byte memory overwrite. And so the way this works is that because it's a linked list, it does an assignment of the previous to the next to remove it from the linked list, and this lets you do a 4-byte overwrite, which I'll cover in a little more detail in a couple slides. And one thing to keep in mind is the heap is a very runtime-dependent data structure. It's very dependent on how the application is running now and in the past. And if, as an attacker, you can control or influence allocation sizes, and when these allocations happen, this will allow you to manipulate the heap and basically line things up to make exploitation much more reliable and much easier. So kind of give a picture to this. On the left, we have an adjacent in-use heap memory block and free block before there's an overflow. So in the in-use block, there's just data there. And the free block has the values for the previous pointer, the next pointer, and so on. And then after we overflow the in-use block into the free block, we choose new values for the previous pointer and the next pointer. And what this will let us do is basically, for one value for the previous pointer, we specify the value. For the next pointer, we specify the memory address that we want to write that value to. This is commonly referred to as what and where. What you want to write, where you want to write it. And one thing to keep in mind for the next couple slides is you don't actually write the memory address of the target. You have to write the memory address that's basically the checksum of the target. The heap was somewhat clever in wanting to prevent or detect accidental heap overflows. Because heap overflows are a big pain, because if you're overwriting past the bounds of a buffer, you don't know when the application will crash. When you have an accidental stack smash, it crashes immediately. On an accidental heap smashing, it just corrupts memory, and then it might crash 5 minutes later, or it might never crash at all. And then you run it again, it may or may not do that. So to make debugging a little useful, they basically, on all heap operations, they, quote unquote, validate these pointers to make sure they haven't been overwritten. And the checksum they use is very simplistic. They make use of the fact that any heap pointer is going to be at minimum to a 16-byte block, so it'll be aligned to a 16-byte memory address, which means that you have 3 unused bits, 3 unused least significant bits that will always be 0. And so they do is they shift and set, which means basically that they can verify a heap pointer just by ANDing it with this value here and making sure that none of those crucial bits, the 2 least significant and the 1 most significant bit, have been overwritten. What they'll do is whenever they do a heap operation, they'll do this to the next and the previous pointer. And to remove the checksum, they just shift and AND. But what does this let us do? If you look at the address space of a process on OS X, there's a lot of interesting things in the lower part of the address space. And these lower addresses have a null byte as the most significant byte. But in other heap implementations, you often can't write to these because you're overflowing via a string operation. The null byte will signal early termination. So you can't do that. However, because of this checksumming, they basically get rid of that annoying limitation for you. What this will let you do then is target these memory addresses that have a null most significant byte and overwrite them if you want. And there's some actually very interesting stuff in there. One is called the imports table. The imports table has function pointers to all the imported functions that an executable uses. So if you can cause a heap overflow, you can overwrite the pointer to printf, and so the next time the application calls printf, you gain control. If the application is written in Objective-C, the Objective-C memory segment in the executable has crazy amounts of information. It actually has the entire Objective-C class structure for the executable. You can overwrite things in here. You can overwrite method pointers, and this will let you gain control whenever an Objective-C method is used. Other malloc regions are stored in the address space with these addresses. These also have function pointers in them. There's a bunch of stuff you can do. So just to review the the classic heap metadata. It's called a write for. This is just writing